All right, so we spoke about t-tests and ANOVAs, and we'll do a little bit more practicing of that in the tutorials and in the computer labs. But what happens when the variable you're measuring is actually not a continuous variable, that it's not like pH or salinity where any number, is a real number. What happens if you have categories that are categorical, ordinal or nominal? So say I'm looking at colors, or whether you're left-handed or right-handed. Okay, so I can ask, I can look at the distribution of my answers to that query, and the kind of hypothesis I would test in this case is it different to a random distribution. So if left-handed and right-handed, if I had the same chance of being left-handed or right-handed, we would have a population of about 50-50, and I can ask myself, are we different to 50-50? I already know that it's not 50-50. I think it's about 10%. Okay, so I'm expecting, if I am to randomly select a group of Monash students, that 10% of them will be left-handed and 90% of them will be right-handed. Unless some people say, and I actually don't think that's the case, but some people say that in science there are more left-handed people. Okay, and then I'm going to take a survey, I'm going to subsample this population, and I'm going to see how many left-handed people there are, how many right-handed. Does that deviate from a 90-10 breakdown, right? So this time I can't be more or less left-handed. There is no scale of left-handedness. There's just an answer which is left or right. Okay, so in this case, two possible answers. In the example we'll do in class, we're talking about M&M colors, right? So we have 5 options. I think it changes all the time. So we have a chi-square test of independence. So basically I'm checking if my sample is different to the expected distribution or expected population. So here's my handedness in class, okay? How many people are left-handed in my Monash classroom, or in a number of Monash classrooms? I need to sample this properly. How many are left-handed in the general population? And I can see I have my expected values this time. I'm going to compare to an expected value. Whether it's boy-girl, right, it would be 50-50 is my expected value. But with this one, I have a priori knowledge that this is the distribution in the general population. So I'm expecting 10 and 90, and I can go and survey and fill these two, right? And now I have a parameter that a statistic I can use to work out whether my observation is significantly different to one that could have occurred naturally by sampling this population. So I can actually randomly sample a population and get 100% left-handed people. I can randomly sample the population and get no left-handed people. And I can randomly sample the population and get a 40-60. But the mean is 10-90, okay? The true, I need to know whether my observation is within that range of the 10-90, or is it different enough to have that 5% confidence that I'm not getting it wrong, that I'm not wrong more than 5% of the time. So this time I have an observed value, and I'm coming back to the eyes in a minute, and an expected value, the difference between those, squared, okay, chi-squared, divided by the expected value. So if I think about I being a row in this, so this time I have 2 options. I goes from 1 to 2. Then I have observed left-handed minus expected left-handed squared divided by expected left-handed plus, that's the summation sign, observed right-handed minus expected right-handed divided by expected right-handed, with the square thing, and all of those together add up to a chi-square. Now, what do I do with the chi-square? I got a number. It's 6. It's a number. I don't know which. Is it big enough to say my populations are different? Again, I'm going to use the same trick with the critical values. I'm going to look at the chi-square distribution, which varies a lot depending on the case. And this time I have left plus right minus 1. I have one option, okay? Because if you're not, so the degree of freedom comes into, this is a good place to explain what it is. If you're not left-handed, you must be right-handed. So really you only have one choice here. Because if you're not that, you're the other. So the degrees of freedom, even though there are 2 options, are just 1. So for a k of 1, this is what the distribution looks like. And I can plot it cumulatively, and I'm looking for that point where 95% of the values, and here is my critical value. And above this critical value, I can reject the null hypothesis. So I can create my own test in R. So this time I have a new variable I've created called C2. I just called it chi-square C2. And it equals the sum, right? Because we're summing, this was the summation of the observed minus expected squared divided by expected, right? I just have 2 here. And now I want to know how the probability of a chi-square of this value with these degrees of freedom, I will get that probability, okay? So this is how we do it in R. I think we're going to do it in the computer lab, so you'll get a better feel. We can do it in R, but we can also open tables. So these probabilities have been calculated already. So you can open a table and see whether your value exceeds that critical value. But what's important to understand all the time with the T, with the chi, is that you have your own statistic that is from your data, and you're comparing it to a distribution that is based on an assumption that the null hypothesis is correct. Okay, so the last thing we'll touch on with hypothesis testing, and I'm sorry we're running through this quite quickly, but we have other things to cover in the unit, is the non-parametric tests. So remember we had a normal distribution, it has parameters, and we can make use of those parameters. It's because of the shape of the distribution we can guess. We can guess where this point is, okay? We don't really need we know what the rejection area is. So this is the area where I reject the null hypothesis. This is the area where I don't. These are those chi's. And if my chi is underneath this critical value, I can't reject it. And I can work all this out because I know the parameters of this distribution. If my data does not fall under normal distributions, or T, which the T distribution kind of mimics, and the F distribution requires normally distributed data, then all of a sudden I'm a little bit stuck. Okay, and I need to use something that does not rely on those parameters, and we call those the non-parametric tests. So what happens is often what gets done is that instead of using my values that are not normally distributed, I just rank them. So I'm losing a lot of information because I'll get, say, A, B, C, okay, treatment A, B, C has a mean of 1,502, 200, and 180 for C, then this is turning into a rank 1, 2, 3. Okay, and I've lost all that information that A is actually much bigger than B. Okay, or B and C are actually not that different. So I'm losing a lot of information by ranking, but sometimes that's what I have to do. So it's a much weaker test. It's much harder to get a significant rejection of the null hypothesis if you're using non-parametric statistics, which is why we often try to force a data to look normal by manipulating its distribution by doing things like transformations of the data. And we spoke about those in, I think, lecture 2 or 3. So all of these things can be done using a rank test, okay? So we're not going to go into them in much detail because of the, it's quite an introductory unit. But there are non-parametric tests. They are the dark side. They are weaker. And we use them when the data is not normal. So, and we use them when the data is ordinal. Okay, sometimes the data just comes in like that, say your SETU scores, right? You're not saying, you're just giving me a 1, 2, 3, 4, 5. You're not saying, oh, she's like a 9.5 out of 10. You know, I mean, like you're just ranking it, right? So 1 is not, 1 and 2 are not, it's not double the quality, right? So I have sometimes data that is ordinal data, so I have to use a ranking test. And sometimes I have a very small sample size. So very small sample sizes, remember the case with the dice, are unlikely to be normally distributed. Okay, so often all we need to do is try to get larger sample sizes. And it's a big consideration when conducting experiments of should I add more samples by, say, removing one of my factors in the experiment, because I do want, I mean, I probably can't take care of more than 200 plants, but maybe I can only measure the effect of salinity and not salinity and light and then end up with only like 3 plants per treatment. Maybe I want to keep it as 10 plants per treatment. We always want kind of to maximize our sample size. So just reminding you that you can ask any question you have, just email. We have office hours as well, and I'll see you soon.